It's been very fascinating listening to yesterday and today's presentation. I would like to also add my late colleague David McKay to this presentation, and you'll see during the presentation the reason for David's addition. He really has a significant discovery which we'd like to report today. Next slide, please. You know, the history of the volatiles in the moon is really the key controlling thing is the solar wind has been discussed in the presentation previously, along with the impact history of the moon. And the solar wind basically bathes the surface of the moon with species that are in the solar abundances, and if there's cold traps, that obviously have the opportunity for these volatiles to go to the cold trap. And this is something that's been around for a long time, since the early 60s, and has been discussed yesterday. Next slide, please. The source of volatiles really is several sources. Not only is the solar wind, but we can have meteoroids and comets bringing volatiles to the surface. We have recently know there's volatiles associated with the lunar magma, and of course the humans' activity on the moon and impact spacecraft adds contaminants. But the water that could be trapped at the poles has been estimated up into the 10 to the 16, 17 grams in these trapped zones, really quite high. Next slide. You know, as we said, the potential sources are described here on this cartoon. Next. The solar wind, you know, as it constantly bathes the surface, you know, it's predominantly hydrogen from the solar wind, but we do have other elements in their solar abundances. And so we have the opportunity for not only hydrogen, but also other volatiles of helium and carbon and nitrogen and other noble gases to be implanted. And we know that the lunar soils can contain up to 1 cc per gram of hydrogen, and which is really quite a large amount. And we can use this for not only chemical processes, but potentially for resources in the future. Next slide. One of the interesting things is once we got humans on the surface of the moon, we began to see things up close. And this is from Apollo 16, and it's at the flag crater with the astronaut there. But the crater that's on the left is a very significant crater. It's a very fresh crater. The astronauts observed how unique in its morphology it was. It will turn out to be one of the most interesting samples that's ever been brought back from the moon. Next slide. So the processes operating in the near surface are not only additional processes from high energy particles, but meteoroids and solar wind and micrometeorites, and all impacting not only the highlands, but the regolith of the Maury basalts. Next slide. So it's a constructional process of the impacts occurring on the surface. So here we have a glass agglutinate from Dave McKay, and we know from the analysis of the agglutinates they turn out to be enriched in this solar wind species, and also retain gases released from the impact process of producing the agglutinate, and these gases are trapped inside the glass within these particles. Next slide. So we also have the loss mechanisms from the photodissociation of molecules once they're in the exosphere near the surface environment. They can be swept away with the solar wind if they don't go to cold traps. The meteoroid bombardment, you know, produces things not only for the gardening, but the radiation materials are trapped there, but the volatile species can be lost. And we know they can be retained in the silicates as the agglutinate enrichments. Next slide. We've been fortunate on Apollo 17 to have a surface composition experiment called the LACE, which is a mass spectrometer which was able to detect volatile species moving across the surface of the moon during the post-dawn events. And also we were able to compare the nighttime and daytime events. We've detected species from not only impacts of other spacecraft, but periodic, that'd be sudden release of water, methane, ammonia, and CO2 from various sources on the moon. This instrument only analyzed gaseous species. Next slide. Now, the history of the volatiles on the moon, as we know, has really changed with the recent detection of water and the melt inclusions. And so this gives us magmatic water along with the water we knew that was from extra lunar sources. For example, the protons are radiating onto the surface. Now we must remember the target of the moon is really nothing but a big sphere of oxygen that the protons are aiming at, because the other cations are in these interstices sites, and they're really just impinging upon oxygen basically. Next slide. Here's a small cartoon down at the kind of the very high resolution scale for carbon. If carbon comes in, it can combine with hydrogen that's also may be in the solar wind, produce simple molecules like methane, which may be retained or may be lost from sputtering processes, and then the reduction occurs that produce the iron blebs that may be there in these small amounts, and as we see in the surfaces of grains that have been exposed to these solar wind and high energy particles. Next slide. The earliest studies of what may be in the lunar regolith was from Apollo 11 samples, and the British group of Jeff Eglinton and published in the paper by Abel sees this whole suite of species that are released upon basically a pyrolysis of bulk lunar samples. These were about a large 5-gram sample, and so they were able to see these large number of species from low temperature contaminants all the way up to the higher temperatures. And some of these we know clearly from production of the proton irradiation were the methanes and the other CH species that were there. Next slide, please. The abundances that we saw from all the lunar samples are given in this table for the 3 categories of soils, breccias, and rocks. And we see for the hydrogen, most abundant species in the solar wind is the mean for soils is really on about 40 parts per million or 40 micrograms per gram. The breccias are enriched up at 68, about 50% more than the soils, and the rocks are down around 2. In the case of carbon, it's similarly, the ranges are about the same. Sulfur, of course, it's tied up in sulfide minerals within the rocks. Next slide. As we heat soil, we begin to see a variety of species coming out as the Abel study showed, but this is one of our first plots from 1970-71 from Apollo 11 soil 10086. And we began heating the soil at 4 degrees C per minute. We saw that low temperature under 150, 200 degrees were absorbed species of nitrogen, some water vapor, but other temperatures around the 400 to 600, we saw solar wind hydrogen evolve, and at higher temperatures above 700, we basically were beginning to get reaction species. Next slide. We have it summarized in the low temperatures are adsorbed atmosphere species. Across the middle is solar wind species, and above 700 degrees are reaction products of the minerals bearing the carbides, sulfides, and all reacting with available oxygens. Next slide. Now, one of the things that was mentioned this morning by Bill Farrell is the possibility of these high energy particles when you have solar flares. In addition to the protons normally coming from the sun impinging on the silicates, should we get a higher energy particle, it would be embedded deeper into the target that it's impinging upon. Here we see the normal release of the hydrogen, H2O, that comes off, and we see that the release in the 600 to 800 degree range there appears to be a small spike that says high energy protons. Perhaps this is release of water or OH that is coming from these higher energetic events coming from the sun, which is just interesting observation that we have there. Next slide. So we can reproduce this with synthetic studies and impact studies of ion implantations, and Lard originally did some of this in the late 60s. We made mixtures of carbides, sulfides, and et cetera, and were able to produce the release profile that was seen for most of the lunar samples. Next slide. So what is the hydrogen abundances on the moon? Well, as we saw earlier, the average is about 36 micrograms per gram. This is for 80 soils. Our lab has probably analyzed 200 to 400 different lunar samples for hydrogen, carbon, nitrogen, and sulfur. But if you look at an immature soil, really it's only down around about 10 to 12 micrograms per gram. The submature is around 35, and the mature is it seems to average out about 45 micrograms per gram. It appears to reach a saturation level of the solar wind there. And it correlates directly with the ISO-FeO indicator of the fine-grained metallic iron and its presence in the soil. That's an indicator of maturity. Next slide. As has been discussed at this meeting, the observation of the presence of variations of OH and water on the moon is clearly an indicator that something is going on involving water and OH on the surface of the moon, being trapped at the poles and shown by the enrichments and all. Next slide. So the solar wind species are really impinge on the grains, and their solar wind are grain and surface area dependent. As seen on the next slide, we have the study that done by the late Peter Eberhard, and he has grain size across the bottom in microns versus the concentration for helium, neon, argon, krypton, and xenon. It's clearly a surface phenomena, and this is, smaller the particles, the more volatiles that are present. Next slide.
Everett, you have about 90 seconds.
Okay, this is a good slide. It shows the variations of various grain size and abundances that are within the soils. You can do the abundances versus how much is there on their weight percent and get mass balance, and things agree on hydrogen. Next slide. Now, as we look at hydrogen on the moon, does it vary with depth? Let's look at the lunar core. Let's look at the 3-meter core from Apollo 17. Next slide. We see that on the core, with depth of 3 meters, its hydrogen abundances are directly correlated with the ISO-SFEO maturity indicator. This is very neat. It's down to about 3 meters, 1-to-1 correlation. Next slide. Then we have samples that may be unusual. This is the 61221 from Flag Crater. This is a sample which was seen to have adsorbed gases on the surface. Next sample. Next slide, I mean. We see the early release of species that are unusual. We see methane, hydrogen cyanide, some carbon dioxide, a distinct weight loss, and this is the lowest maturity soil returned from the moon. We proposed and published in Science that it could be cometary residue or impacts adsorbed on the surface. Next slide. Where we asked the question, do we have any evidence that we have any volatiles that have altered from the impact of the primary silicates? Next slide. It's possibly, and here's why. Next slide. Within the samples that Dave McKay analyzed in November of 1969 is a lunar phyllosilicate. This clay is in Apollo 10-0086 soil. Dave took this sample, put this photograph over into a group of photos that says, unusual, look at it later. Unfortunately, Apollo 12 came along, and this is typical of a phyllosilicate that we see from water interaction with primary silicates. What we see similar to the Martian meteorites with water interaction with silicates. Next slide. We have other soils like the orange glass soil and the green soil. Next slide, with the maturity of those, very clearly it's surface related. The volatiles are there, not with the maturity. Hydrogen goes 1-to-1 with the depth. Next slide. Now as we're moving to the end here, we look at the rocks. We know there's only 1 to 2 micrograms per gram hydrogen in the rocks. Very low abundances. Next slide. One of the most interesting, fascinating things is the variation of hydrogen versus mineral composition. Here we have a plot of hydrogen versus ISO-FEO for Apollo 16 samples. And clearly those that are in orthocytic rich, next slide please, are above those that have the Apollo 17, which are circles with no, which are circles, not the solid fill. And clearly the titanium-rich materials, like have ilmenite, retain hydrogen to a greater degree than in the orthocytic rich material. Clearly, in mafic composition retains solar wind hydrogen better than in lunar rich. And these need to be taken into account for other studies of the moon as we go into this. So what we've seen is on first hand, the sample studies indicate that we have variations within composition, variations within maturity indicators, and I think the studies of the ground-based truth, which is the samples, must be taken into account with any remote measurements and processes that have been proposed to be operating on the moon. Thank you.
Thanks, Everett. While I'm asking these questions for people, would the next speaker please get ready? So we have a question from Mike Poston. What is the abundance of carbon on the moon, and is there a source of new carbon today?
Okay, let's start with the target material. Basalt composition is typically less than, I would have to say, 15 to 20 micrograms per gram. Typically, it's very low. Breccias, they're up around 40 to 50 weight parts per million. And you look at soils, it varies depending on the history of the soil. Now, you asked the question, is it the second part of the question is it varying today?
Or is there a source?
Is there a new source of carbon? Of course, we have meteoritic material and cometary material coming in on the moon all the time, and so it is an ever-changing environment. And whether it's changed over time, we don't really know. But as we look at the chapters of the book that we see going back in the lunar cores, we see there's clearly indications that carbon abundance is varying over time as the variation of carbon typically goes with the isotope FeO.
Okay, it looks like there's a bunch of people trying to ask a question, but they're not coming in.
Everett, you can go ahead then and answer questions in the chat room as we continue on.
Yeah, it's
No
time for
problem.
us to move on.